Welcome to the lecture on turbulence modeling, which is a part of our tips and tricks webinar series. The agenda for the next 90 minutes is as follows. This lecture will start with a brief introduction to turbulence in general. Then we discuss what is turbulence modeling and why we need it, followed by some discussion on popular modeling approaches including statistical approach or RANS and scale resolving approaches like large eddy simulation and detached eddy simulation. And then we summarize the lecture. Before we begin, we need to put an important disclaimer. The reason being, this subject of turbulence modeling tends to be an uncomfortable mix of deterministic and semi-empirical laws, which obviously encourages the formation of distinct groups, each with its own doctrines and beliefs. For example, engineers promote the use of semi-empirical models which might not be of interest to mathematicians. So any discourse on turbulence modeling must carefully pick its side, resigned to the fact that not everyone will be satisfied by the outcome. That being said, the primary goal of this lecture is to provide an insight into foundations and principles underpinning different turbulence models, discuss their assumptions, calibration, limitations, and advantages. And hopefully this insight will help us make more qualified decisions on turbulence models. And moreover, there is really an interesting story to our progress in turbulence modeling so far. And this is the story I will try to unpack through this lecture. So let's start from the very beginning. What is turbulence? Well, we have tried to answer this question for over a century now. Several engineers, physicists, and mathematicians have tried to come up with the theory of turbulence, but without much success. So it is now generally agreed that there is no single coherent theory of turbulence. There are many problems and many theories. One relevant to boundary layers, another to stratified flows, and so on. Nevertheless, this concerted effort has helped us build a reasonable picture of turbulence. We understand what causes turbulence, and we can easily recognize it when we see it. So what causes turbulence? Turbulence is a manifestation of fluid's reluctance to flow along smooth and steady path when exposed to shear while flowing at modestly high speeds. High speeds means my flow is convection dominated and viscous damping is too weak to kill any fluctuations, which can eventually grow to turbulence. And we can easily identify certain distinct characteristics of turbulent flow. Invariably, across all turbulent flows, we observe wide range of length scales which are inherently three-dimensional and accompanied by vorticity, dissipation, and enhanced mixing. As a result, turbulence can drastically affect our engineering quantities of interest like pressure drop, heat transfer, drag, and mixing efficiency, to name a few. It also dictates the spreading rates of jets, wakes, and boundary layers, flow separation, size of separation zone, transport of particles, bubbles, and droplets. So there lies the importance of this subject in general and modeling and simulation of turbulence. So we do understand some characteristics of turbulence, but how do we numerically simulate it? The good news is that we have deterministic equations for fluid motion, including turbulence. Perhaps we are not that lucky with the soil mechanics, polymers, and even some multi-phase flows. The bad thing is that Navier-Stokes equations are nonlinear and do not permit analytical solution for arbitrary geometries and boundary conditions. That's still fine because we can solve these equations using computers. We do it all the time for similar problems in mathematics, physics, economics. But the ugly part is extensive computational resources are required to numerically resolve turbulence accurately, even for simple flows like flow through a channel, flow around a cylinder, and hence not feasible for practical engineering applications. A recent estimate is that even if the compute power continues to increase at the current rate, a fully resolved calculation of an aircraft will not be feasible for the next 70-80 years. What does that mean? That means some level of approximation and modeling is necessary to bring down the computational cost. hence the need for turbulence modeling. And then various modeling approaches with increasing complexity are possible depending on accuracy and cost trade-offs. And these are essentially statistical or scale resolving techniques where a subset or all of turbulence is approximated by some semi-empirical methods. And the most popular ones are direct numerical simulation, large eddy simulation, and Reynolds average Navier-Stokes equations or RANS. In DNS, we solve the Navier-Stokes equations as it is. That is, no modeling is involved. So technically DNS is not really a turbulence modeling approach. In LES, we directly resolve the large energy containing scales of turbulent flow and model the smaller eddies. While for RANs, we model the entire spectrum of turbulent scales. And if I look at my energy spectrum here, all scales are resolved in DNS, while all scales are modeled in RANs, and LES lies in between. As we move from DNS to RANs, the amount of modeled content and hence empiricism increases, but the cost decreases. And that's typically the goal anyways. And even within each approach, there is no one single model that works for any general flow, hence leading to the development of a large number of RANs, LES, and hybrid models. And we will discuss these different modeling strategies starting with the simplest and most popular approach, the statistical approach or RANs. As engineers, we are mostly interested in average quantities like average mass flow rate, pressure drop, drag, etc. So even if DNS were possible or we could afford DNS, one would average the solution obtained to find these mean quantities. So why not solve for mean quantities directly? And that's why any analysis of turbulent flow inevitably invokes a statistical description. That is, look for equations for the mean flow. But unfortunately, there are no exact governing equations for the average flow, and empirical modeling becomes necessary. One might imagine that an equation for the average velocity could be obtained by averaging the equations for the instantaneous velocity, but that would work perfectly fine if these equations were linear. But Navier-Stokes equations are non-linear. But since we want to work with these mean quantities and average flow, we desperately need these equations. So we try it out anyways. So let's see what happens when we average the governing equations. Time and space dependent flow variables such as velocity, pressure can be decomposed into mean and fluctuating part. And when we substitute this decomposition into the original Navier-Stokes equations and time average it, we get this equation which is known as Reynolds average Navier-Stokes equation, which is almost identical to the original Navier-Stokes equation but with this additional unknown term. So what just happened is the averaging of a nonlinear term created these new unknowns without any new governing equations. And this is the penalty we pay for not explicitly resolving the highly unsteady turbulence field. So if I look at my equation again, the first term in this bracket is the viscous stress term. So the second term is naturally interpreted as turbulent stresses, or more formally Reynolds stresses. And now this is essentially the task of different turbulence models, at least RANS models, to calculate these turbulent stresses, which can be now fed back into this RANS equation to close the system. But to develop those models, we need to first understand what are these stresses, what drives them, so that these drivers are major elements of any model we come up with. The best starting point to gain insight and construct an accurate turbulence model is perhaps the set of governing equations for the Reynolds stresses themselves. That is, track the evolution of these turbulent stresses. So let's try that. And this is essentially the first turbulence model we discuss, the Reynolds stress transport model. So we can try to close the system by deriving 6 new equations for the 6 turbulent stresses. 6 because this stress tensor is symmetric. The equations can be derived by a relatively straightforward mathematical procedure. So essentially you multiply the Navier-Stokes equations with the fluctuations and time average it. We get the equations for Reynolds stresses. Though the process to get these equations is relatively straightforward, the equations themselves are not. So we get this seemingly cumbersome equation referred to as Reynolds stress transport equation. Usual terminology is indicated on the right. And the left hand side term is just the local rate of change of Reynolds stresses, which arises from the imbalance of terms on the right hand side. And each of these terms represents a physical process contributing to stress budget at a point in space. If we look at the first term, this is the turbulent diffusion of Reynolds stresses due to velocity and pressure fluctuations. Second term is the viscous diffusion of Reynolds stresses. The third term is the rate of production of Reynolds stresses because of its interaction with the mean gradient. The fourth term is rate of destruction of Reynolds stresses, and the last term, perhaps the most interesting term, is pressure strain interaction term. Interesting because pressure fluctuations act to scramble the structure of turbulence and redistribute turbulent stresses among components to make turbulence more isotropic. So this mechanism is by no means local. Okay, great. We have the Reynolds stresses. Now we can feed this information back to our RANS equations and close the system. And our work here is basically done. Not really. The reason being, this is not a closed system of equations for the second moment or Reynolds stresses. While molecular diffusion term and rate of production are known terms, the remaining three terms are unknown. Since both these terms have just the dependent variable and mean gradients we are anyways calculating for, if we look at turbulent diffusion term, it has now unknowns of even higher order. We have third order unknowns in turbulent diffusion term and also pressure velocity fluctuation interaction terms. So we can still make some educated guesses on the turbulent diffusion term and dissipation term, but we do not really have a good idea about the pressure strain interaction term. It's even difficult to set up experiments to validate any models we come up with. So now essentially this is the task of RSM submodels to account for these three different terms, or we can try to derive equations for these higher order terms as well. So we derived new equations for the Reynolds stresses. Each equation involves third moment terms as unknowns, and third moment equations can be derived in a similar fashion, but it introduces another set of fourth order unknowns and so on. So we see a pattern here. So we started with the first moment or mean equations and we got second moment terms as unknowns, and we tried equations for second moments or Reynolds stresses and got third moment terms as unknowns. And if we try equations for third moments, we'll get higher order moments as unknowns. So we already see it's not going in the right direction. And this is essentially the turbulence closure problem, which highlights a very interesting irony that we have deterministic equations for turbulence, but the solution is chaotic, hence difficult to resolve. We know the average solution is smooth, but we cannot get the equations. But despite this red flag, if you still wish to continue on this path, good luck, and maybe we can learn from your exercise and experiences. What we essentially learn is it's impossible to develop a predictive statistical model simply by mathematical tricks. And this closure needs additional information which is ad hoc in nature by design. Nevertheless, increasingly higher moment equations should capture more physics and leave less to modeling. So even if these equations are not used as it is, these help us understand the interaction between turbulent stresses and mean gradients, and we can come up with simpler but more qualified models. To summarize the RSM model, this is the most complete physical representation, at least in the RANS framework, though the model complexity makes verification a bit challenging. RSM is also able to capture complex strains like swirling flows, secondary flows, rotation, etc., and hence can predict flow anisotropy to some extent. And for some swirling flow applications like cyclone separators, RSM is the only accurate closure in the RANS framework, and some simpler models can actually produce completely unphysical results. But the flip side is RSM is computationally expensive and numerically stiff. These different Reynolds stress equations do not get along very well and don't reach an agreement easily, or in other words, convergence is generally slow or sometimes difficult to secure. And now, since we are working with the higher order moments, RSM is less forgiving to low quality meshes compared to simpler models. And we already discussed that pressure strain interaction term is the most challenging one, and there are a bunch of different options or models available to handle that term depending on the application you work with. And to model this term in star CCM plus, 4 different approaches have been implemented: linear pressure strain model, quadratic pressure strain model, linear pressure strain 2-layer model, and elliptic blending model. The bottom line is, for most engineering applications, we cannot afford to run RSM. Even if we can, it does not behave very well numerically. So we look for a compromise on accuracy for cost. That brings us to eddy viscosity models. The idea is, rather than solving these 6 additional transport equations for the Reynolds stresses, can we not just link them to some known quantities like mean strain rate, mean vorticity? Buznick proposed, yes we can. The key concept is that at molecular level, momentum is diffused by viscosity and appears in the governing equation as viscous stresses. Similarly, the momentum diffusion by turbulent eddies can be modeled by effective eddy viscosity. So we can link our Reynolds stresses to mean gradients through a variable eddy viscosity. So in other words, we are assuming that the net effect of turbulence is just added viscosity. But unlike molecules, the eddy size and shape are strongly dependent on local flow properties. Hence, eddy viscosity is not a fluid property but a flow property. So this approximation is more likely than not a crude one. And the system is not closed yet, so we have simply pushed the task of determining the Reynolds stresses to now determining eddy viscosity. Now this poor fellow eddy viscosity has to tell us the whole story of turbulence, or more precisely, tell the mean flow to behave in a turbulent manner. And so all RANS models of this category or eddy viscosity models will try to find a route to estimate eddy viscosity accurately, often through analogy, intuition, and empiricism. So what I mean by that is, we discussed analogy already. So we are linking our Reynolds stresses to mean gradients through eddy viscosity. But how do we calculate this eddy viscosity? Either we somehow magically know its value, or based on our intuition and dimensional analysis, we can express eddy viscosity as a product of a length scale and a velocity scale. And this is not a unique combination of variables. Many other recipes are possible. I can have a velocity square and time, kinetic energy and time, and length square and gradient, and so on. No matter what variable combination we use, we will have to invoke empiricism or look to experiments to determine these proportionality coefficients. And this one slide is essentially soul of any turbulence model. These are the steps we go through to develop any turbulence model, at least in the context of RANS. And we can guess that from analogy, intuition, and empiricism, multiple approaches are possible, and we'll discuss some of the most common and instructive. And moreover, increasingly complex and accurate models can be developed, which improve upon older and simpler models. The simplest possible approach is to directly prescribe eddy viscosity. That is, somehow I know the local distribution of eddy viscosity, and hence no transport equation for the eddy viscosity is solved. So these are known as zero equation models or algebraic models, because eddy viscosity is prescribed algebraically and no equation is solved. In an attempt to capture more physics, we can solve additional transport equations for the turbulent quantity, usually turbulent kinetic energy, and those are known as one equation models. And the next level would be solving for even more transport equations, hence two equation models. And there are even these half equation models like Johnson-King model, where an ordinary differential equation is solved for eddy viscosity. But we'll start with the simplest one, the algebraic or zero equation model. So remember, we stole the idea of linking these Reynolds stresses to strains from kinetic theory of gases. And there is no reason to stop there. Why not replicate the fluid viscosity calculation in the kinetic theory of gases to eddy viscosity calculation here, and which led Prandtl to propose this idea of mixing length. So mixing length is very similar to a mean free path in thermodynamics, and if we can somehow come up with a representative length scale for eddies, we can calculate eddy viscosity from this relationship. But we don't know this mixing length. For relatively simple shear flows like jet, wakes and boundary layers, we expect this mixing length to be proportional to the width of the shear layer, but the empirical coefficients will vary from problem to problem as we go from boundary layer to jets and wakes. And for more general flows, this mixing length varies locally and is highly problem dependent. So even if we have an extended mixing length database from several experiments, an algebraic prescription of length scale will remain inadequate to represent this highly three-dimensional, unsteady and non-local turbulent eddies. For example, at the center line of this jet, the elevated levels of turbulence are due to convection from upstream and diffusion from these highly strained regions on the periphery of the jet. But if I look at the mean gradient, it's 0. So based on this mixing length relationship, I'll get an eddy viscosity 0. But in reality, my eddy viscosity is closer to the peak value at the center line. So that means we are missing some critical transport mechanism in this simple model. So we need models which will account for this transport, and the simplest models that do that are one equation models. So in order to model non-local effects, we need to transport some quantity. And since we are working with eddy viscosity, why not transport the eddy viscosity itself? And from our derivation of Reynolds stresses earlier, we learned that it had convection, diffusion, production and destruction terms. So Knee and Kwasny proposed a transport equation for the kinematic eddy viscosity. And they try to model diffusion, production and destruction of eddy viscosity based on some educated guesses. But since its introduction at the Stanford conference in 1968, this model was never very popular. Perhaps the primary objection was that the transported quantity, the eddy viscosity, is not a fundamental physical quantity, it's a model quantity. So we are trying to come up with a model equation for a model quantity. But still, this objection did not discourage the development of a very similar model but extremely popular model, the Spalart-Almaraz model. So Spalart and Almaraz devised a one equation model based primarily on empiricism and dimensional arguments. It uses a variable which is very similar to eddy viscosity, but it behaves linearly near wall, so hence facilitating the numerical solution. It also uses some sort of damping functions next to the wall to calm the turbulence near wall. And this model was designed and optimized for flow past wings and airfoils, and in some cases it performs even better than most advanced models for applications it's designed for. For example, 2D airfoil profiles and attached boundary layers. But as we move away from those nicely attached flows, it starts to struggle. Another advantage of this model was that it's easy to implement in any type of grid. Structured, unstructured, single block, multi-block. But still, it's not suitable for general purpose code. For example, it struggles for internal flows, jet flows, partly due to lack of length scale information, and it also lacks transport information for rapidly changing flows. So these one equation models are a significant improvement over algebraic models by including transport through convection and diffusion terms. And there are other one equation models as well which solve for transport equations for turbulent kinetic energy, but then need a prescription for length scale to close the system. And even models like NK and SA, which we discussed, are closely tied to thin shear layer assumptions, which is implicitly equivalent to prescribing a length scale. And moreover, the transported quantity is still not a fundamental physical quantity but a model quantity. So logical step would be to come up with an evolution equation for more physical quantities which are closely tied to our fluctuations, which leads us to two equation models. The idea is again to model non-local and transport effects. And as we discussed earlier, we can express eddy viscosity in terms of a velocity and a length scale. And it seems natural to use turbulent kinetic energy as the basis of velocity scale, because higher the TKE, higher is the momentum exchange and higher is the eddy viscosity. And turbulent kinetic energy is defined as half the trace of Reynolds stress tensor, or simply the sum of these normal stresses. So once we have decided that we are going to use turbulent kinetic energy as the basis of our velocity scale, we can express our eddy viscosity now in terms of turbulent kinetic energy and a length scale. And now the closure problem has been shifted to determining K and L. And these two equation models are complete models in the sense that they can predict properties of a given turbulent flow with no prior knowledge of turbulence structure. They are in fact the simplest complete models of turbulence. While for one equation model, we'll still need to provide some length scale information directly or indirectly. But in contrast to velocity scale, we do not have an equation for the length scale. And purely based on dimensional reasoning, several length scale surrogate variables can be employed for which we can derive the equation. For example, dissipation rate, specific dissipation rate, entropy, and so on. Which one we end up using will depend on how well behaved these variables are physically and numerically. So let's start with the most popular variable, the dissipation rate or epsilon, or by far the most popular two equation model, the K epsilon model. So this model uses transport equations for TKE and dissipation rate to calculate the eddy viscosity using this relationship. This model is marked with the influential contribution in the late 60s and early 70s, though it's generally associated with Jones and Launder's paper of 1972 and often referred to as standard K epsilon model. So to calculate eddy viscosity, now we need turbulent kinetic energy and epsilon. So we derive equations for these variables. We can derive the equation for turbulent kinetic energy by contracting the Reynolds stress transport equation, or by simply substituting I is equal to J. And after some simplifications, we get this equation for turbulent kinetic energy with familiar terms on the left hand side. The first term on the right hand side is diffusive transport. The second is rate of production of turbulent kinetic energy because of its interaction with the mean gradient, and the last term is rate of destruction of TKE. So you may notice that the production term still contains Reynolds stresses, which is easily linked to the mean flow through Buzynsk approximation. So this term is known. We have also introduced another unknown in the diffusive transport, the turbulent Schmidt number, sigma k, essentially assuming that the turbulent diffusion of k is driven by the gradient of k itself. And we also expect the diffusivity of k to be closely related to the diffusion of momentum. So this sigma k is of the order of 1, and that is indeed the value used by most models. The last term is rate of destruction, and this is still an unknown term for which we will try to derive another transport equation. So let's try that. We tried, but we were not very successful. To be precise, we can actually derive an equation for the dissipation rate, but it contains too many unknowns to work with. So instead, we ended up using some mathematical and physical reasoning to come up with the model equation for the dissipation rate. So it can be derived by multiplying the k equation by epsilon divided by k and introducing these model constants. When we do that, we get most terms identical to K equation divided by the time scale K over epsilon. The implicit assumption is that rate of production and destruction of dissipation are closely linked to the production and dissipation of TKE. And also similar gradient diffusion approximation is made for this diffusive transport. Now K equation is rigorously derived and is more physical and well behaved, while dissipation equation is a model equation and pure invention. So this is a weak link which will come back to haunt us. Also, in the process of deriving these equations, we have introduced a bunch of constants. And now how do we find these constants? And you probably already know the answer. We'll look to experiments, or in other words, invoke empiricism. These constants can be calibrated through experiments and some rare analytical solutions which invariably tend to be simple shear flows. For example, we can use the analytical solution for decay of isotropic turbulence in uniform stream and get C epsilon 2, and also from measurements for thin shear layer fully turbulent boundary layers at local equilibrium, we observe that production balances dissipation rate and my shear to TKE ratio is 0.3, which gives us C mu. And it also gives us a relationship between the remaining constants for which we can use computer optimization to calculate those constants. And we already assumed that sigma k value is closer to 1. With these calibrations, the model should perform reasonably well for flows that are not very far removed from these calibration scenarios. And this calibration process is demonstrated for this just K epsilon example, but similar procedure is followed for other models as well. To summarize the standard K epsilon model, so this model is by far the most popular eddy viscosity model, which is widely validated and works well for internal flows. And standard K epsilon model does very well in predicting turbulent shear flows, but it struggles in adverse pressure gradients and highly strained flows including rotation and streamline curvature. As a result, it performs poorly for separated flows. Moreover, it's rather difficult to be integrated through the viscous sublayer. We will discuss that in detail in the following slides. And these limitations are well known and are related to the insufficient physical description. And K epsilon comes in countless flavors which try to improve on older or simpler models, and we will discuss some of those popular variants next. Since the standard K epsilon model was tuned with reference to relatively simple equilibrium flows, we should not be surprised if it struggles with the non-equilibrium flows, to the extent that it can permit negative normal turbulent stresses in highly strained flows. For example, in a strongly accelerating flow, if we look at this equation for the streamwise normal stresses, if the streamwise mean gradient is very high, it will give us negative normal stresses. And negative normal stresses are called unrealizable state because no real statistic can have negative variance. Now we can address this issue right here by limiting our eddy viscosity such that my normal stresses are always positive. Or in a more general sense, I can make C mu sensitive to mean gradients rather than constant so that my normal stresses are positive. And that's exactly what we do in a realizable K epsilon model. So this modification ensures that the normal stresses are positive, and it also satisfies this mathematical constraint known as Schwarz's inequality, which essentially means that my cross correlations are never perfect. And the fact that C mu is no longer constant but local flow dependent, this model is expected to perform better for flows under strong adverse pressure gradients, separation and recirculations. But remember, this is a kind of a band-aid solution to constrain the Reynolds stresses to more physically plausible values and does not really address the real underlying causes of unrealizable stresses. In addition to that, the dissipation equation is also handled slightly differently with modified source and sink terms, while K equation is identical to the standard K epsilon model. So note these coefficients are now mean strain rate dependent, and this leads to more physical turbulent stresses. To summarize a realizable K epsilon model, it is built upon the robustness of a standard or vintage K epsilon model, and it provides results at least as good as classic model, but typically better in complex flows. And as a result, it is the default recommendation in mainstream commercial packages, and therefore represents the most proven, well quantified and widely documented of all closures. And performance is substantially improved for non-equilibrium scenarios like planar and round jets. So it addresses the round jet anomaly, boundary layers under strong adverse pressure gradients and separation, and other non-equilibrium flows like rotation, recirculation, and streamline curvature. Okay. Before we move to other turbulence models, let's discuss perhaps the biggest challenge in turbulence modeling: the challenge of capturing near wall turbulence. The primary reason I would like to bring it up now is that the following models will try to address this challenge in one way or the other. Now, from an industrial point of view, an accurate prediction of near wall turbulence is critical, since quantities of primary interest are usually those evaluated at the wall, for example, skin friction coefficient, heat transfer coefficient. And in most cases, wall is in fact the source of turbulence, and production and dissipation of turbulence will peak closer to the wall. But most models derive from measurements or theories which are valid for homogeneous flows and not too close to the wall. The primary reason being that generally this region is very small. For example, in external flows, the boundary layer thickness can be several orders of magnitude smaller than the characteristic length scale, so making measurements extremely difficult if not impossible. So our understanding of this region remained fairly limited until recently, when DNS became possible or affordable, and that too for relatively low Reynolds numbers, simple shear flows. So this still remains an active area of research. To better appreciate the complexity of structure of turbulence near wall, let's watch this short video. So this is a visualization of the structure of a turbulent boundary layer by isocontours of negative lambda, which are color coded by wall distance. And this is a result from DNS calculation using 8 billion cells and run on 4,000 cores. Okay, the animation itself looks really cool, but in terms of fluid mechanics, what is so special about near wall turbulence? First, the no slip condition on the wall imposes strong mean gradients near the wall. It also imposes near wall damping on fluctuations and Reynolds stresses. But wall normal fluctuations experience stronger damping due to wall impermeability condition, as illustrated by this plot for the turbulent stresses near the wall. from a DNS result of a channel flow. While the wall parallel stresses fall quadratically, wall normal stresses fall 2 orders of magnitude faster towards the wall. So this illustrates the turbulence is highly anisotropic near the wall. Another characteristic feature is that the size difference between the energy containing and dissipative eddies gradually decreases as we approach the wall. And capturing this extremely complex near wall behavior is still a key challenge in turbulence modeling. The eddy viscosity models are not able to capture this wall anisotropy, and we need excessively refined grids to resolve near wall flow features, because now larger scales are of the same order as my dissipative scales. Now you may ask why we worry so much about the turbulence near wall. What about the mean flow? How does it naturally behave near wall? The answer is, after using Reynolds decomposition, this effect is inherited by both mean velocity and fluctuations. But in computations, the blocking of mean velocity is well reproduced, since we explicitly impose incompressibility on the mean flow. We solve for continuity. The same is not true for fluctuations, since we just incorporate turbulence through eddy viscosity. And the blocking effect must be accounted for by other means. And let's see how we accomplish this, at least in the eddy viscosity framework. The most common approach, or the low RE approach, is to apply damping functions to some or all of the coefficients in the model. So these damping functions modulate the coefficients as a function of turbulence Reynolds number, often incorporating this wall distance. Second approach is two-layer approach, which solves different equations near wall for one or both the variables. And the third, perhaps most accurate and interesting approach, is elliptic relaxation or blending approach. That is, solve additional equations to naturally account for wall effects without damping functions. And several models incorporating damping functions have been proposed in literature, and 2 have been implemented in star CCM+. Standard K epsilon low RE model and AKN low RE model, Abe Kondo Nagano model. And standard K epsilon low RE model is recommended for natural convection type of problems, particularly when YAP correction is invoked, while AKN is useful for more wider applications and complex flows. Difference is essentially in the form of these damping functions, so you can see here. And notice the dependence on turbulence Reynolds number or wall distance y in these functions. Second approach is two-layer approach. In this approach, the computation is divided into 2 layers, and in the layer next to the wall, the dissipation rate and eddy viscosity are specified as a function of wall distance, and then these are blended smoothly with the values computed from solving the transport equations far from the wall. So this is lambda is a sort of blending parameter, and the K equation is solved in the entire flow. And several types of these two-layer formulations have been proposed, and 3 have been implemented in star CCM+, 2 for shear driven flows, and the last one is for buoyancy driven flows. And note the dependence on wall distance again. And this explicit specification of a dissipation rate and eddy viscosity is no less empirical than damping functions approach, and the results are often as good or better. Now, rather than using these ad hoc damping functions, can we come up with a better or more physical way of resolving near wall effects? In this case, Durbin said, yes, we can. Recognizing that the envisaged wall blocking effect on pressure fluctuations is non-local and is felt further away from the wall, Durbin proposed elliptic relaxation of the pressure strain term for the full RSM model. The key argument in this model is that the most critical property missing from homogeneous models when modeling non-homogeneous flow is the elliptic nature of pressure. So in this model, damping is enforced through differential elliptic equations rather than algebraic expressions in terms of wall distance. So as a result, the model does not require the wall distance computation and is better defined for complex geometries. And we save a bit in terms of computational overhead as well. And it also ensures correct asymptotic behavior for different Reynolds stress components. That was the primary goal to begin with. The flip side is it requires 13 transport equations, 6 more for this relaxation tensor or Fij and 1 for dissipation rate. And in addition to that, it suffers from numerical difficulties with boundary conditions for Fij tensor. So remember, we gave up on a Reynolds stress model a long time ago for its cost. We cannot afford to solve too many transport equations. And simpler models are often used in practical computations, which motivated Durbin to propose a modified version of this model, but in the eddy viscosity framework. So which is more commonly known as V2F model. So in this case, the system of equations for the Reynolds stress tensor is replaced by a transport equation for the velocity scalar or wall normal stresses and an elliptic equation for the relaxation function. So this function is similar to a redistribution term. The objective of this model is to retain the near wall stress anisotropy but to embed it in a more computationally tractable formulation. And it also implicitly states that the relevant velocity scale near wall is wall normal fluctuations rather than turbulent kinetic energy. To summarize V2F model, this model is designed to capture near wall effects like separation, reattachment, stagnation, and as a result it reproduces correct behavior of eddy viscosity near wall without the need of damping functions. But still it's an eddy viscosity model far from the wall and is not able to capture the effects of curvature, rotation and secondary flows. Also, it's computationally expensive due to 2 additional equations, and the F equation still poses some challenges in terms of boundary condition implementations and convergence. So another compromise was proposed by Hangelich in the framework of RSM to completely get rid of F equation, which was giving us a lot of trouble, and replace it by a simpler scalar equation that reflects the elliptic relaxation only notionally. So it solves an elliptic equation for a blending function alpha, which is 0 at the wall and 1 further away from the wall, and reducing the number of equations from 13 to 8. But it is still an RSM model and comes with associated cost and challenges. So for a more code-friendly version, Billard and Lawrence more recently extended this blending idea to Durbin's V2F model, hence leading to this elliptic blending K epsilon model. So we see how we are learning from previously developed models and then trying to improve in terms of incorporating more physics into them or simplifying those models for more practical purposes. And even in this elliptic blending approach, we work with a simpler variable. So it's a normalized variable which gives better control over boundary conditions. And it predicts correct asymptotic near wall behavior, that is accounts for the viscous and non-viscous wall blocking effects. And it shows significant improvement for internal flows, predicts better separation and reattachment, and shows improved universal near wall behavior. And this model is available in both the flavors RSM and K epsilon and is numerically more robust. So we have discussed the K epsilon model in detail. Now let's go back to our list of surrogate variables and see if we can try something different. How about the second variable in the list, the specific dissipation? And this brings our discussion to the last eddy viscosity model we discussed today, the K omega model. The idea in fact predates K epsilon model. The first proposal for two equation model was made by Kolmogorov in the early 1940s, and his choice of variable was specific dissipation rate, that is dissipation scaled by turbulent kinetic energy, and that was purely based on intuition and dimensional reasoning. But it was Wilcox's version that became more popular. So this model solves the transport equation for specific dissipation or inverse of time scale in addition to the K equation. Now the specific dissipation or omega is epsilon divided by K. That means it's singular at the wall or no slip boundaries. So despite this apparent drawback, it was shown that this model can in fact be integrated to the wall without the requirement of any modifications or wall functions or wall damping. And this is a remarkable property compared to K epsilon model, which does not behave very well near wall. And this improved behavior near wall can be attributed to a few key elements in the model. The generally chosen coefficient, the turbulent Schmidt number, is 2, while in K epsilon model it is closer to 1, and this higher value reduces the transfer of TKE from buffer region to the near wall region, and hence producing more physical behavior near wall. Another reason is extra dissipation is produced near wall in this model. The most significant advantage of K omega model is that now it can be integrated to the wall without further modification, and it achieves a higher accuracy for boundary layer flows with adverse pressure gradient. The standard model can be used in this mode without requiring computation of wall distance, so which helps us a bit in reducing the computational cost. While the main disadvantage is that it's extremely sensitive to inlet boundary conditions for internal flows or free stream conditions for external flows, a problem which does not exist for K epsilon models. To the extent that a small change in inlet conditions or free stream conditions can change my solution significantly. And it also tends to overpredict separation. And then later Wilcox revised his original model to account for these several apparent deficiencies. And Mentor tried to address these fundamental limitations by blending the K omega model with the K epsilon model. So Mentor recognized that the dissipation transport equation of K epsilon model can be transformed into an omega transport equation by just simply substitution of variables. And when we do that, what we get is an equation which is very similar to the omega equation in K omega model, but with an additional cross diffusion term. So Mentor proposed that a blending function can be used to include this cross diffusion term far from the wall and not near the wall. So this approach effectively blends the K epsilon model in the far field with the K omega model near wall. And one may argue that this blending function crossover location is arbitrary, and that is still open for debate. For the sake of completeness, these are the equations for K omega and the blending functions. And this seemingly intricate function is simply an operational device to interpolate between K omega and K epsilon model. So to summarize, this approach cures the biggest drawback to applying the K omega model to practical flow simulations. And this model has seen fairly wide application in the aerospace industry, where viscous flows are typically well resolved and turbulence models are generally applied throughout the boundary layer. And this model has been validated against many other applications such as turbomachinery blades, wind turbines, and etc. Essentially, SST model does a better job than K epsilon model in predicting separation and reattachment, though it struggles a bit in capturing buoyancy effects or complex internal flows. Okay, so going through these different linear eddy viscosity models, we have learned that there are some inherent limitations to these models. Maybe this stress-strain relationship is not as simple as assumed by Buznisk. So as a result, these linear eddy viscosity models are unable to capture the turbulent stress anisotropy, secondary flows, curvature effects, etc. For example, the fully developed flow through ducts with the non-circular cross-section. These weak secondary flows exist in corners, which can greatly impact skin friction and heat transfer at the wall. And a purely diffusive linear eddy viscosity model fails to capture these flow features. And this is not even a complicated geometry. From an engineering perspective, it probably doesn't get simpler than this. Also, the streamlined curvature can enhance or suppress the production of turbulence, which is again not accounted for by linear eddy viscosity models. And moreover, as we discussed earlier, it tends to overpredict TKE in the stagnation regions and so on. So the obvious conclusion is to look for models with more accurate stress-strain relationship. And how do we do that? Well, we can always go back to the exact transport equations of Reynolds stresses or differential RSM. We can start at DRSM, and through some clever mathematical tricks, we can convert these equations into a set of algebraic equations or ARSM. But still, these are a bunch of equations which are numerically stiff and computationally expensive. And learning from ARSM, we can try to come up with an explicit relationship for the stresses. That is, we can link these Reynolds stresses to terms we were already using in the linear eddy viscosity models, but now we have these higher order terms in mean strain rate and mean vorticity. And the hope is that as more higher order terms are included, we expect this model to capture more physics like anisotropy, curvature, rotation, and so on. And if instead of going through these steps of DRSM, ARSM, and then coming up with an explicit ARSM model, we had directly come up with an expression like this, we would call it nonlinear eddy viscosity model. So that means the boundary between EARSM and nonlinear eddy viscosity models is very fuzzy. These are essentially the same models, but the difference is in the path we took to develop them. And in star CCM plus, we have these models available in both K epsilon and K omega flavors. So here is an example of a quadratic constitutive relationship with the results shown for a flow in a rectangular duct. So what it shows is that SST model with the quadratic constitutive relationship, QCR, is able to reproduce the secondary flow features where the base SST fails. And the results are almost identical to the full RSM model. And moreover, SST plus QCR is able to capture this near wall anisotropy, that's significantly different normal stresses in QCR, where linear eddy viscosity model just shows one curve. Okay, so let's end our discussion of eddy viscosity models by revisiting the wall again. So we learned that one of the most challenging aspects of turbulence modeling is capturing the near wall variation of turbulent quantities. A very fine mesh is required with the first cell centered around y plus is equal to 1. And for most engineering applications, it's not feasible to resolve this layer. So it would be nice to bypass this region completely whenever possible through some simplifications or assumptions. And of course, this would only be possible when my near wall flow field is closer to some known solution. And one of those known solutions is that in a near equilibrium boundary layer for zero pressure gradient, the mean velocity profile follows a log law in a part of the boundary layer, while it's linear right next to the wall. and there is a region in between which we are not very sure of, known as the buffer region. Now we can directly use this profile without resolving the near wall region, hence enabling us to use a coarser mesh with the first cell centered in the equilibrium or log law region, which is typically valid from y plus is equal to 30 to 500, and this range can be much larger for very high Reynolds numbers. But there are two serious concerns with this shortcut. The first is that this log law assumption is valid for a very specialized flow conditions of attached boundary layer, zero pressure gradient, and hence not applicable to non-equilibrium flows like stagnation, separation, recirculation, etc. So we might actually have to switch back to this finer mesh for those type of flows. The second problem is that the y plus is a flow dependent quantity, and it's difficult to ensure fixed y plus values for all near wall cells. And we run into the risk of having y plus in the buffer region where we do not know the profile. So to address that issue, we have this blended approach, which assumes a blended linear and log law profile. So irrespective of where your first cell centered lies, we can still use this blended velocity profile. And please note that this is different from modeling wall damping as we discussed earlier. There we were trying to model the turbulence near wall. Here we are trying to skip it altogether. And now some recommendations for near wall treatment. Always use all y plus, especially when it's difficult to achieve a pure high y plus or low y plus mesh. Use a low y plus treatment when we are really interested in near wall velocity profiles or heat transfer, or boundary layer tends to separate due to adverse pressure gradients, and we have enough resources such that simulation time and cell count is not a critical issue. Use a high y plus approach when wall bounded effects are not a priority or separation is expected only due to sharp changes in the geometry. And simulation time and the cell count are a critical issue. Just a brief comment on unsteady RANs. Unsteady RANs or URANs is a reasonable approach as long as there is a clear distinction between the large scale mean flow unsteadiness and fluctuations. For example, transient boundary conditions, where typically the time scales are much larger for the boundary condition than the fluctuation time scales. But one needs to be careful when these mean unsteadiness timescales start overlapping with the fluctuation timescales. In some cases, URANs may not even be a valid approach then. Another case is when fine turbulent scales are dominant factor in the simulation, or these scales are themselves responsible for larger scale fluctuations. Then we have to resolve these turbulent structures, which brings our discussion to scale resolving approaches, and we start with large eddy simulations. And this approach is really useful when we have enough computational resources, or in some problems it's critical to capture more of unsteady turbulent flow features. For example, when we want to study aeroacoustics, vibrations, VIV, etc. So what is large eddy simulations? Let's say we don't have a supercomputer or enough resources, but we want to run DNS. Well, we can run DNS on a coarser mesh than required for the DNS. Basically, we are solving the Navier-Stokes equations as it is without any modeling on a coarser mesh. And this coarser grid is able to resolve the larger eddies in the flow, but not the ones which are smaller than a cell or two. But in reality, there is an interaction happening between all scales of motion all the time. So the results for the larger scales would generally be wrong without taking into account the influence of smaller scales. Now, if we could somehow magically account for this missing information, we can run a poor man's DNS, or more formally known as larger dissimulations or LES. And the models that account for this missing subgrid information are called subgrid models. So in RANs, all turbulent scales are modeled and model calibration determines accuracy. So it's a post-dictive process. While in LES, we attempt to faithfully resolve up to 80 to 90% of turbulent structures, and it's more likely a predictive process. So the primary motivation is that the larger eddies extract energy from the mean flow and are highly anisotropic and vary from flow to flow, problem to problem. Whereas the smaller eddies dissipate this energy and are relatively isotropic or universal, meaning they can be easily modeled. So the idea is of spatial filtering using a low pass filter rather than time averaging. So for example, if we start with this fully resolved image and apply a low pass filter, that is cut off the higher wave numbers, we get an approximate image. But we still get a decent idea of the original image. But as we keep on decreasing the cutoff wave number, we lose a lot more detail. Eventually, we are unable to recognize the original image. So that means there is a cutoff wave number above which we can still reconstruct the missing information, at least approximately. But how do we decide on that cutoff wave number? At least in the context of turbulence, we are lucky that there is a concept of inertial subrange. So if we revisit our energy cascade and spectrum again, the idea is following. The largest eddies are created by the inertial instabilities and are problem dependent. And these are themselves subject to inertial forces and break up into smaller eddies. And these smaller eddies to yet smaller eddies and so on. And there is a continuous cascade of energy from larger to smaller scales. And the smallest scale is where the viscous effects dominate and eddies dissipate to heat. And these smallest scales are known as Kolmogorov scales. Kolmogorov hypothesized and experiments confirmed that at sufficiently higher Reynolds number, there exists a range of wave numbers where energy is neither produced or dissipated, but simply transferred from larger scales to smaller scales. In other words, these small scales are somewhat passive and simply mopping up whatever energy is passed to them. So if we cut this energy flux pipe at some intermediate point and provide a proper dustbin of energy flux, then perhaps the larger scales will not even notice the absence of smaller scales. And that is the primary goal of the subgrid stress models, to dissipate the correct amount of energy transferred from the larger scales. And in a well-resolved LES, the boundary between the resolved and unresolved scales is situated in the inertial subrange. So mathematically, one starts by filtering the Navier-Stokes equations to obtain the equations for the larger scales. And while doing that, we immediately realize that the non-linearity of Navier-Stokes equations will prevent us once again to get the exact closed equation for the filtered variables. And again, a term similar to Reynolds stress term is produced, and this needs to be modeled, in this case known as subgrid stresses. And similar to what we did in RANs, we can try to model it using subgrid viscosity. And we can use this subgrid viscosity to link our subgrid stresses to filtered gradients. Now the remaining challenge is to calculate the subgrid viscosity from a model called subgrid stress model. So the main approximations we make in LES compared to DNS are the subgrid scale dynamics and near wall flow behavior. Hence the models that account for these approximations are critical to the accuracy of LES, which are subgrid stress models and near wall models. The most popular subgrid stress models are Smagrinsky model, dynamic Smaglinsky model, and wall adapting local eddy viscosity or Weyl model. Smaglinsky model is by far the oldest and best known subgrid scale model. So it can be considered as a LES version of mixing length of Prandtl. So what we are doing here is we are linking our subgrid viscosity to filtered gradients through a length scale proportional to the grid size. So we already know where this is going. Now we need to tune or find this Smaglinsky constant as we did for C mu. Though typically a constant value of 0.1 to 0.2 is used for the basic Smaglinsky model. And in its basic form, the Smaglinsky model is the simplest subgrid model. But the model coefficients require adjustment in shear turbulence, transitional flows, near solid surfaces flow, essentially for the flows for which that constant was not calibrated. Also, it needs this ad hoc Van der Waals damping function for wall bounded flows. That means the wall distance calculation is required and hence leading to increase in computational cost. And therefore this model should be avoided for large scale computations on complex geometries. It's however useful for reference simulation since it is the original algebraic subgrid scale model formulation. And moreover, this model is also absolutely dissipative and it cannot account for backscatter of energy, that is the transfer of energy from smaller scales to larger scales. Another problem is that it can predict non-zero subgrid viscosity even for laminar flows. And many of these limitations are due to a constant value of Smaglinsky coefficient. So we would like to calculate this coefficient from the calculated flow field dynamically. And there is a very clever trick in how we do that in the dynamic model. So the idea is to determine CS parameter from the smallest resolved field. So one can employ a test filter larger than the LES filter. And if we assume that the Smaglinsky model will hold on both the filters, we can express the subgrid stresses in terms of the same constant and filtered gradient. Similarly for the LES filter, same constant square and known filtered gradients. So we also notice that some of the unresolved stresses for the test filter are actually resolved stresses for the LES filter. So whatever my test filter is actually trying to guess is already available through the LES filter. So that means we can try to calculate CS from this resolved stress. So that means we can use this information to calculate CS, or in mathematical terms we can invoke this rare identity in turbulence known as Germano's identity to get an equation of CS in terms of resolved field. So this slide is for a more mathematical curious audience with some details, but the bottom line is you can express the Smaglinsky constant in terms of known or filtered quantities. To summarize the dynamic Smaglinsky model, now the coefficient is no longer a user input but calculated by the model, and it's able to capture near wall turbulence damping to some extent. And now negative coefficient is possible which can model the backscatter, but typically that's avoided by imposing a non-negative value on the total viscosity because it leads to numerical instability. And it's also computationally expensive compared to Smaglinsky model because we are solving a couple of more equations. So moving on to wall adapting local eddy viscosity model or Weyl model. And this is the least computationally expensive subgrid stress model. Uses a slightly more involved subgrid viscosity equation than Smaglinsky model. And as a result, it automatically gives accurate scaling at the walls without the need to calculate wall distance. And it also suffers from the same limitation as Smaglinsky model, that the model coefficient is not universal. But still it is less sensitive to the value of coefficient than Smagrinsky model. Also, this model gives zero eddy viscosity for laminar flow regions and can potentially be used for studying relaminarization. So as a result of all these advantages, it is the default or recommended subgrid model in star CCM+. Okay, so we need to discuss near wall turbulence again for the last time, now in the context of LES. So LES of a boundary layer is dominated by the need to resolve the fine structures near wall. And this is illustrated by this plot of number of points required to resolve a boundary layer. While the outer layer resolution is nearly independent of the Reynolds number, the inner layer requirement increases rapidly with the Reynolds number, and hence it dictates the overall cell count. The primary reason being near wall, the larger eddies are also of similar size to the dissipation scales now. So the near wall resolution requirements are as severe as DNS. For example, in a boundary layer with the Reynolds number of a million, 99% of the grid points are spent on resolving less than 10% of the boundary layer. So even if we use some sort of near wall modeling known as wall modeled LES, it is still very expensive. So it's natural to look for ways to bypass this region completely. The answer is detached eddy simulation, which is hybrid RANS and LES approach. The idea is of RANS treatment of the attached boundary layers in its entirety, while LES is applied to regions of massively separated flow. That is, only the detached eddies are simulated using LES, hence detached eddy simulations. But how do we make this switch from RANS to LES? And that's the primary challenge in DES. Since Pollard was using a length scale, so he proposed that we can modify this length scale to make this switch. So he introduced this DES length scale, which is minimum of wall distance and C delta. That means next to the wall it's D and away from the wall it's C delta. And so which means near the wall U RANS, assuming coarser grid near the wall, and C delta away from the wall. That also means there is a direct impact of grid spacing on this switch. So that's why DES models require more carefully crafted grids. So what happens if we over refine the grid near wall? So if my mesh is too fine next to the wall, then minimum of D and C delta is C delta. That means switch to LES in boundary layer. But that is not the original intent of DES model. We would like to switch to LES only outside the boundary layer. So this is a problem because the mesh is fine enough to switch to LES but not fine enough to resolve LES content. So this results in underprediction of subgrid stresses known as modeled stress depletion, or in case of separated flows, it leads to early separation known as grid induced separation. Because lower eddy viscosity would lead to lower momentum diffusion near wall and hence early separation. Also of concern is smooth transition to LES from RANS. So even if this switch happens in the boundary layer. So now these two models are trying to calculate the solution in the log region and may not agree with each other at the location of this switch. And this agreement is known as log layer mismatch. So we try to address the first problem by delaying the switch to LES. So this in principle can be avoided by shielding the RANS model from DES formulation for wall boundary layer, or in other words, delaying the switch to LES, hence delayed detached eddy simulation. And this was proposed by Mentor, who used the blending functions of SST model to identify the boundary layer and prevent an early switch to LES. So following Mentor's idea, Pollard later proposed several modifications to the original DES, including shielding functions which depend only on the eddy viscosity and the wall distance. So it therefore in principle can be applied to any eddy viscosity based DES model. And there might be situations when I want this switch to happen in boundary layer, when would that be needed? Okay, let's say I have incoming turbulence from an upstream obstruction or the inlet, and I can afford a bit finer mesh in the boundary layer. Then I would like this switch to happen in the boundary layer. Or in other words, I want to use DES or DDES as a wall model for my LES. But DES does not work well when it is used as a wall layer for wall modeled LES. Obviously, this was not the original intent of the model, and it results in relatively strong log layer mismatch between the RANs and the outer LES region. So we need to address the issue of LLM to use it as a wall model. So it was proposed that DDS can be developed into a suitable wall modeled LES, resulting in the formulation of what is known as improved delayed detached eddy simulation, or IDDS. The IDDS model features several rather intricate blending and shielding functions which allow using this model both in DDS and wall modeled LES mode. In StarCCM Plus, we have DDS and IDDS available with both SA and SST models, and recently we implemented DDS with the EBK epsilon as well. And as we discussed earlier, we expect this model to perform better in capturing the near wall behavior. And it's also compatible with all Y plus and low Y plus treatment. And it also has an important property of predicting transition to turbulence and separation better. Just to demonstrate that, let's look at a classic test case, the flow around Ahmed body. So this is an example case where the rear slant angle is 25 degrees while the critical angle of separation is 30 degrees. So we do not expect separation. So if we calculate the flow around the Ahmed body using SST IDDS and EBK epsilon DDS, what we find is that SST IDDS predicts separated flow from the slanted surface, which in experiments is attached. EBDDS predicts attached flow as expected from our earlier discussion, since it captures the near wall flow better. And obviously this overprediction of separation in SST IDDS can be attributed to the underlying RANS model, which is SST. So this is essentially a complete picture of turbulence models available in StarCCM Plus, and there are certainly further sub-models and sub-options, but this is kind of the big picture. And this is to summarize some general recommendations for each model. But my primary goal in diving deep under the hood was to help users come up with these best practices or recommendations on their own. So I do not plan to go through these in detail. Okay, to summarize the lecture, we are committed to providing the best-in-class turbulence models in StarCCM Plus, and a good choice of turbulence model is key to accurate CFD results. And StarCCM Plus has a wide range of turbulence models suitable to all classes of flows and computational budgets. And moreover, turbulence modeling is still an active area of research. New models will keep coming in this area, and once those models are mature enough and validated enough, we will try to add them to the menu, primarily to ensure that StarCCM Plus users continue to have access to the state-of-the-art tools for their engineering simulations. And some acknowledgements for people who I was in touch with for preparing these lectures, and some online resources for my comics. And of course, it's impossible to cover everything on turbulence modeling in a short lecture. So we intentionally focused on the fundamentals, which should be common and useful to all our users. A full course on turbulence will need days, if not weeks. And thank you very much for your time in attending this lecture.